Welcome back to the Explainer. Today, we're going deep underground, literally, into China, to unpack a massive breakthrough that is happening right now. We're looking at the Jiangmen Underground Neutrino Observatory, or JUNO, and the audacious quest to solve one of the absolute biggest mysteries in modern particle physics. Okay, let's dive into this, because the scale we're talking about here is just absolutely mind-bending. Trillions of these nearly massless particles, called neutrinos, are passing right through your body every single second. They're everywhere, yet they interact with matter so rarely that just catching them, let alone trying to weigh them, is essentially like trying to catch a ghost. So our cosmic detective story today is broken down into 4 parts. First, the ghost particle mystery. Second, the mass hierarchy problem. Third, inside the Juno machine. And finally, the global neutrino race. Let's start with part 1, the ghost particle mystery. You know, neutrinos emanate from the sun. They rain down from our atmosphere via cosmic rays, and they literally pour out of nuclear reactors. But as they travel, they do something completely counterintuitive. So the crucial point is, they don't just pick an identity and stick with it. They come in 3 types, or flavors: electron, muon, and tau. As they zip through space at near light speed, they morph. They oscillate between these flavors. Imagine throwing an apple, right? But halfway through the air, it turns into an orange, and by the time it's caught, it's a pear. That is essentially what is happening right now on a quantum level. The bizarre part is that each flavor doesn't actually have a definite mass. It's this weird quantum mechanical combination of 3 different mass states. And these mass states evolve at different rates. Think of them like intermeshed gears of different sizes turning at different speeds. As the gears turn out of sync, the overall flavor of the neutrino changes. So an electron neutrino born in the sun can cleanly evolve into a muon or tau neutrino, and then morph right back again. Which brings us to part 2, the mass hierarchy problem. This is the exact puzzle physicists are desperately trying to solve. Experimenters already know that 2 of these mass states are close together in weight, and one is quite different. But because neutrinos are just too incredibly small to measure directly right now, we don't know the exact order. Actually, scratch that. We don't know the hierarchy. Are there 2 light mass states and 1 heavy one? Or is it 2 heavy mass states and 1 light one? It might sound like a minor detail, but knowing this specific hierarchy is a master key for modern physics. The stakes for figuring this out couldn't possibly be higher. Sorting these neutrinos by mass is absolutely crucial for unlocking some incredible cosmic secrets. It determines whether future experiments can figure out if the neutrino is its own antiparticle, which would really help explain how they get their tiny masses in the first place. But beyond the quantum scale, solving this hierarchy is critical for understanding the explosive mechanics of supernovas and even mapping the macroevolution of entire galaxies. Let's zoom out a bit for part 3, inside the Juno machine. So, how do you solve a quantum problem that spans all the way from subatomic particles to the scale of galaxies? Well, you build a $300 million machine deep underground. At the absolute heart of the Juno experiment is an enormous plastic sphere, standing roughly 10 stories high and measuring a full 35 meters in diameter. It's a literal engineering marvel. And inside that colossal sphere sits 20,000 tons of a very specific, specially formulated liquid. This liquid is designed to do one thing perfectly. It flashes with a tiny bit of light whenever certain charged particles zip through it. It acts essentially as a giant, ultra-sensitive tripwire for the universe. But to catch those incredibly tiny flashes of light, the outside of the sphere is lined with exactly 43,183 phototubes. And the Juno team couldn't just go out and buy these off the shelf. The required efficiency was so unprecedented that the team actually had to invent a completely new kind of phototube, and they built their own factory just to manufacture them. So how does this all come together to actually detect a ghost particle? Let's move to Susan and see how this builds step by step. Step 1. An electron antineutrino gushes out of a nearby nuclear power plant reactor. Step 2. It travels 53 kilometers straight through the Earth to the Juno detector at near light speed. Step 3. Very, very rarely, one of these uncharged ghosts actually strikes a proton right inside that liquid sphere. And step 4, that collision turns it into a positron, which travels about 10 centimeters and radiates a measurable flash of light. By measuring the total energy of that light flash, Juno can precisely calculate the original neutrino's energy. And that energy measurement, that is exactly where the magic happens.
You see, Juno is achieving an unprecedented 3% precision on the neutrino spectrum. That's twice as precise as any previous detector. The spectrum of neutrinos hitting the detector peaks at 3 mega-electron-volts, then it flattens into this mesa shape due to the oscillation of those two close mass states we talked about earlier. But what Juno is specifically hunting for are small, tightly spaced ripples sitting right on top of that mesa. The way those specific ripples shift is going to definitively reveal the mass hierarchy. And the most exciting part is, we're already seeing them. After just 59 days of high-quality data collection, Juno has already reduced the uncertainty on 2 of the key oscillation parameters by a third. And as neutrino physicist Patricia Volley notes about those crucial ripples on the spectrum, quote, they're pretty pronounced. The team essentially hit the nail on the head and got high-quality physics data right on their very first shot.
All right, on to our final section, Part 4, the global neutrino race.
Now, Juno's early success is a massive achievement for sure. But make no mistake, there is an intense international competition to permanently map this hierarchy. While Juno uses a massive liquid sphere to catch reactor neutrinos, major global players are taking a completely different route. Japan's Hyper-Kamiokande, or Hyper-K, and the United States DUNE project are building huge accelerator-driven experiments. Physicists note that once it's up and running, DUNE should be able to determine the mass hierarchy very quickly, making the ordering as clear as night and day.
But the real differentiator right now is the timeline. And this brilliantly illustrates where things stand. As of 2026, Juno is already publishing incredibly precise first results and seeing those telltale ripples. Meanwhile, Japan's Hyper-K won't start taking data until 2028, and the US-based DUNE project won't even receive its first neutrino beam until 2031. It's a true scientific race, but for now, Juno has clearly secured a massive first-mover advantage. We are watching real-time, groundbreaking physics unfold right before our eyes. The mass hierarchy of neutrinos might sound like a niche quantum problem, but remember, it holds the absolute keys to the mechanics of supernovas and the evolution of entire galaxies. So, will these tiny, shape-shifting ghosts ultimately rewrite our understanding of how the universe evolved? Well, it's now just a matter of time and data. Thank you so much for joining me for this explainer, and keep your curiosity focused.